Jai Hind everyone. I am Ankita Sharma. I work here as an assistant professor in electronics and communication department in Ajay Kumar Garg Engineering College. So today it's my second lecture of complex topic. The topic of my lecture is 8085 pin diagram and demultiplexing of address bus. So this is the pin diagram of 8085. It is a 40 pin IC 8085. So here are number of pins X1, X2, we have these two pins as a crystal oscillator, reset out, SOD, SID is serial out data, serial in data, trap to INTA, these are our interrupts, AD0 to AD7, time shared or multiplexed address and data buses, VSS is our power supply, A8 to A15 are higher order address bus, S0 is status signal, S1 is also status signal, read by write bar, these are control signals, ALE is our address latch enable which is used to demultiplex these pins that we'll be discussing in lately here. Input output memory bar, through this pin we understand the microprocessor is working with input output or memory. Ready pin, when the microprocessor is ready, reset in, clock out, hold and HLDA, these two pins are used for the DMS signals and VCCs are ground. So data bus AD7 to AD0, it carries the least significant 8 bits of address and data bus. So AD7 to AD0, these carry, we can say A7 to A0, that is lower order address bus, and D7 to D0, that is the data bus, that is, it is of 8 bit. The address bus, the higher order address bus is A15 to A8, it carries the most significant bits, MSBs of memory or input output address. The data bus has 8 signals, A15 to A8, these are unidirectional. It is not time shared, and other 8 address bits, we can say, which are AD7 to A0, here you can see in our pin, here these AD0 to AD7, these 8 pins are time shared with address and data. So AD7 to AD0. These are bidirectional pins because we use it as address, lower order address and data at the same time. During the execution of these instructions, these lines carry the address bits during the early part. During the early part, you will get to know further in timing diagrams as well, that this during the earlier part of instruction, these pins will be used, the higher order address will be used, and lately it will be used for execution of 8-bit data bus. So this will be used in earlier part, the lower order address, and the direction and the data bus will be used lately, because when the microprocessor will get an address, so first the microprocessor will need an address to fetch the data. The data will be fetched lately, but the primary requirement will be of a memory address, of a address, you can say. The higher address, the higher order address can be picked by A15 to A8, and the lower order address will be picked by the lower order address bus, that is A7 to A7 to A0. So the next is, in order to separate the latch from the data, we can use a latch to save the value before the function of the bits change. So this will be discussing in the demultiplexing of the address bus, which we will be covering here right now. So control and status signals, there are signals which is used to identify the control of the microprocessor, or you can say the nature of the operation which the microprocessor is doing. The control signals are read bar, write bar and ALE. Read bar, it indicates the selected input output or the memory device which is used to be read, and microprocessor is ready for accepting the data available on that bus. Suppose there is an input device, it is giving the data to the microprocessor and microprocessor is ready to read that data. How will microprocessor get to know about the reading? This pin will be active low. This pin will be active low. Why? Because read bar, write bar, these are active low pins. Active low means there is a bar here. It is a complement. Bar means complement. So if it gets 0, 0 complement 1, it will be active. So that's why it is called as active low pin. Read bar and write bar, these both pins are active low pins. So the right signal, this signal indicates that the data on the data bus is have to write, the micro have to write it on some memory or some input output location, on input output device you can say. Next is ALE, it is a positive going pulse. Positive going pulse means it will generated as this. This will be our ALE in timing diagram. When this ALE is 1, at that moment of time, it will, when the pulse is high, it will indicate address. Which address? A7 to A0, the lower order address. And when the pin is low, here, the data D7 to D0 will travel. This is the difference between these two pins. So ALE is equal to 1. ALE is equal to 1. Then A7 to A0. And ALE is equal to 0. At that time, D7 to D0. So जब ALE 1 होगा, then we will be taking the address, lower order address, and when the ALE is 0, the multiplex, the time shared bus will act as the data bus. So this is the machine cycle. These are the machine cycle which a microprocessor can process. These are the status and these are the control signals. 3 control signals are there for microprocessor 8085: input output memory bar, S1 and S0. Input output memory bar, it is used to differentiate between the input output and memory operations. Suppose the microprocessor is dealing with the memory, then memory, here you can see that memory is an active low signal. When this pin will get 0, suppose IOM bar is 0, that means the microprocessor is dealing with the memory, and if this pin 1, the microprocessor will be dealing with the input output. So if I talk about this machine cycles, opcode fetch, this is the first machine cycle, the very first machine cycle on which the microprocessor works. Suppose the instruction is there and the instruction is add, we have to add something. So what will the microprocessor do? It will just fetch the opcode. Opcode means the operation code. If the microprocessor will get to, if the microprocessor will just pick it, the add instruction, it will get to know that, oh, we have to add that. So add will be the opcode, and further whatever the registers, whatever the data is there, that will be the operands for that. So the prime requirement, the prime machine cycle, the first machine cycle for the microprocessor is the opcode fetch machine cycle. In opcode fetch, it will be getting that, it will be taking that data from the memory for sure, because microprocessor don't have its own memory. So that's why it is 0. And in microprocessor, in opcode fetch, it will be reading and writing both. So that's why reading and writing both. So that's why read bar, and it is not writing firstly, it will just read that data. So that's why it is 1. And INTA, there is no interrupt, that's why it is 1. Memory read, where it is dealing in memory. 1, 0, it is reading because it is memory, read signal is there. Likewise in memory, it is here 0. In write, memory write, it is the write bar, active signal, control signal. In input output read, it will be 1 for the input output. Now interrupt technology, there is an interrupt. Suppose if we are doing the microprocessor is doing the main program, it is having the same main programs with particular sets of instructions, and some interrupt come in between, then this signal will be activated. So the microprocessor will just acknowledge it, that's why it is here. In halt, hold and reset, there will be high impedance state for that. The high impedance state is the try state. At that time, the pin is not connected to supply nor to the ground, it is in high impedance state. So the power supply, there are two power supplies needed for this 8085 microprocessor. There are two power supply signals, VCC and VSS. VCC is our plus 5 volt power supply and VSS is our ground signal. There are three clock signals here, X1, X2 and clock out. X1, X2, these both are crystals and these are crystal oscillators that are connected to a small crystal, to an external. It is like this. These are two pins, X1, X2. It is connected with this crystal. When it vibrates, it passes some frequency, the clock frequency. This is our X2, this will be our X1. At that time, suppose the microprocessor 8085 needs approximately 3.2 megahertz frequency. For that, we have to take the value 6 megahertz. It will be divided by 2. Why? Because there are two pins here. We have two oscillators here. That's why two crystals here in this. These two pins, X1, X2. This is a crystal in X1, X2. So it will be approximately like this. So next is clock out. This signal is used as a system clock for devices connected with the microprocessor. The internal clock generator is 3.125 megahertz internally, and for externally we have to do this and it will be divided by 2 like this. Next is serial input output signal. There are two serial signals, that is SID and SOD, serial input data and serial output data line. The serial output data line is set and reset as specified by the SIM instruction that will be covering lately. SIM instruction, set instruction mask, reduce instruction mask. So these are two instruction sets. The data on this line is loaded in the accumulator whenever a RIM instruction is executed. So internally and externally initiated these signals, interrupts here are, we have 5 interrupt signals in 8085 microprocessor. These are TRAP, RST 7.5, RST 6.5, 5.5 and INTR and INTA bar. INTA bar is an acknowledgement signal. Suppose the microprocessor is getting an interrupt request and the microprocessor has solved that problem, that has resolved that interrupt, and it will just pass that interrupt acknowledgement signal. In that case, this signal is transferred. Next is reset in. Reset in is, this signal is used to reset the microprocessor by setting the program counter to 0. Now what was the program counter doing? Program counter was just having the information or address about the next instruction which the microprocessor have to execute. If the program counter is 0, that means the microprocessor will not execute anything. It will be resetted from 0000. So the program counter is resetted. That means whatever the data was there, it is gone. Reset out, this signal is used to reset all the connected devices when the microprocessor is reset. All the devices, which devices? The peripheral devices, we can say input output devices, all the devices which are connected to the microprocessor. Next is our ready pin. This signal indicates that the device is ready to send and receive data. If ready is low, if this pin is low, then the microprocessor will wait for ready to go high, and after that the microprocessor will work. Hold, it indicates that the another master or another device is requesting the use of address and data buses. Hold and HLDA, these two signals are used by the DMA signals. DMA signals contains different signals, different peripherals, different programmable devices. Here are some 8257, 8255. These are DMA signals. These are DMA controllers, we can say. These are controllers. And with that, if they need some help with that address and data bus, at that time, this pin will be activated. And when this CPU has acknowledged this hold request, it will just set HLDA low. So next is our demultiplexing. What is a demultiplexing? Demultiplexing of address bus. The address bus which was AD7 to AD0. Before that, one thing we just missed, the interrupt signals. Here are 5 interrupt signals we have: TRAP, RST 7.5, 6.5, 5.5 and INTR. INTR is the interrupt request. The interrupt request which the microprocessor got from the outside. And trap. Trap is the non-maskable interrupt. Suppose there is an interrupt to which you cannot mask, you have to deal with it. The microprocessor will have to deal with it at any cost. It will be trap, as the name suggests, trap. Next is reset, RST 7.5, 6.5, 5.5. These three interrupts are vectored interrupt. They have their particular address. If this interrupt comes, that means the microprocessor will have to go to that particular location and have to deal with the interrupt. So again, back to the demultiplexing. Demultiplexing is AD7 to AD0. AD is address and data. Bit number 7 to here, address and data. Bit number 0. These are time shared. Earlier we have discussed these are time shared, or we can say multiplexed. Now we have to learn how to demultiplex them. So the address bus has 8 signals, A8 to 815, which are unidirectional. The other 8 bits are multiplexed, or we can say time shared, with 8 data bits. So the bits AD0 to AD7 are bidirectional, and these can serve as both. So during the execution of the instruction, these lines carry the address bits, the lower order address bits, and in the later parts of the execution, they carry the data bits. In order to separate address from the data, we use a latch to save the value before the function of the bits changes. So a latch is used to save the data, because the data bus, there are some T states in the timing diagram of the microprocessor. For 3 T states like T1, T2, T3, and this will be T4. For almost 3 T states, the address bus is used, and for the last T state, the data bus is there. So data bus just got a very less time, so there are highly chance that the bits change, the data bits change. To avoid that, demultiplexing is there and a latch is used. From the above description, it is obvious that the AD7 and AD0 are serving as a dual purpose, and they need to be demultiplexed to get all the information. The higher order bits of the address remain on the bus for the 3 clock periods that we have discussed just now. 3 clock periods, T1 to T3 clock periods, or T states we can say. And the low order bits remain only for 1 clock period, that was T4. And they would be lost if they are not saved externally, and the low order bits of these addresses disappear when they are needed the most. So for that, to make sure that we have the entire address for the full 3 clock cycles, we will use an external latch in that case to save the value of the data bits, or we can say the AD7 to AD0 when it is carrying the address bits, and we use the enable latch for that, that is ALE. ALE is address latch enable. In pin diagram we have discussed this, address latch enable pin. When this pin was 1, it was carrying the address, and when this pin was 0, it was carrying the data. So given that the ALE operates a pulse during T1, which we have just discussed now, like this, a pulse is there, at that time the address is saved, and further it is paused, it is used as the data bus. That's why we call it a bidirectional data lines, because both the purposes are solved here. How it is possible? This is a microprocessor 8085. It has AD0 to A15 pins. If I talk about the A15 to A8, there is no problem regarding the higher order address. The higher order address can run smoothly. It has a separate 8 lines for these upper 8 bits. The problem is there in the lower order address and data bus. For that, we will be using the ALE, address latch enable. So we are taking here a latch, and a latch is further consists of a D flip-flop. There is an inverter, inverted output for this, it is grounded. There is ALE which is used for enabling the D flip-flop. So what is the function of D flip-flop? It just gives you the same output as input. If the input is 1, the output will be 1. If the input is 0, the output will be 0. Like this. This is the D flip-flop. The output will be Q, and here it is inverted output, and it will need some enable pin or clock, you can say, at that time. So this particular arrangement is for all the 8 lines. For one line it is shown here, it is shown for only AD7 to AD0 here. Only for AD7 to AD0 it is shown here. The AD7 is traveling, it is the input in D flip-flop, the enable pin is 1, the ALE is 1 here. Then what will happen? D flip-flop is active, it will take this AD7, suppose at AD7 it is 1, suppose it is 1, so at AD7, 1 will be here at input, at output it will be inverted, Q bar is there, so it will be 0. Here it is an inverter, bubble is there, it will invert it, the 0 will become 1, here it will become 1, and here it is will become 1. So 1 was the input, 1 is the output. How? It is A7 now. All this will happen for all the 8 address lines. All these lines will be our low order address bus. Next, suppose enable pin is 0. If this pin is 0, then this latch will not. Why? Because D flip-flop need a clock pulse to process something. So if this is not working, that means these are not working for this. So from here D7 will go, D6 from here, D5, D4, likewise D3, D2, D1 and D0. So this will be our data bus, that will be from D7 to D0. The summary is, if ALE is 1, the address will be there. The time multiplex AD7 to AD0 will be used as the address, lower order address. It will take the lower order address, and if ALE is 0, at that time this will not work. This D latch, D flip-flop, this latch, this whole latch, it is a latch. It will not work, and D7 to D0, the data bus will be used. So the AD7 to AD0 will be used as the data bus. Thank you.